All right, so welcome for today's office hour. And just as a matter of comment, general comment, as we know, today we started working on fatigue this last week, and then we will continue to finish this area of failure this coming week. And that will be the final step in starting to put together the process of comprehensive shaft design. So I think we will have the last couple of weeks of the course on comprehensive shaft design, including gears and bearings and assembly and so forth. And as far as the project is concerned, I did have the chance to grade most of the reports, and I think by this weekend I should be able to grade the remaining parts, the remaining reports that we have. It looks like everyone is on track. I gave some feedback on the reports themselves, so you can try to improve the final report based on these comments. And I think it will be very interesting the last few weeks putting together basically optimization and failure analysis, so we can bring in what we learned in the course to the progress to the report itself. Okay, so what I have is I have a little review of a few problems that I felt are of importance. So the first one, I have a couple of comments on Castagliano's theorem and how it is used, because it turned out to be that this is this area needs a little bit more attention. So in this problem here, we have a force concentrated at point B, and it has 15 pounds. And then we want to compute the displacement of the tip B in the direction of the force, and also the displacement vertical and horizontal. I think we went through similar examples before, but this is a quick one. So in this case, what we need to do is find the, we divide the component into sections. So we have a section here, OA, and a section here, AB. And in each section, we compute store the elastic energy, and then we take the derivative to get with respect to the force in the direction of the force to obtain the displacement. So this is kind of the general procedure. So we compute the second moments of area, the polar moment of areas for a solid circular section is twice the first moment of area, the second moment of area. And then we start taking moments. So the force is decomposed into one horizontal component 0.6, and then one vertical is 0.8. The vertical is 0.8, and the horizontal is the vertical is 0.6, and the horizontal is 0.8. And then what we do, the comment here is that if I go to the section AB, which is here, and this section here, then I can just compute the moment. I can choose a coordinate, and the coordinate is here, is chosen as X bar. And then the coordinate that I chose, the point that I wanted to make, is that it doesn't matter whether you start from B towards A or A towards B. It's only a matter of convenience. So in this case, we have it from B towards A, and we call it X bar. So the moment is dependent on X bar, and then the derivative of the moment with respect to the force. Then we drop the force out. We have the X bar still left in here. Now, when we go to the member OA, which is here, OA, then we have the moment is computed as 4.2 times F, and we have an axial force because we decompose. This is just due to the horizontal, so the horizontal gives you an axial force. So you have both a moment and an axial force, and both of them you're going to use in the displacement calculation. The same thing for the other component, the vertical component of the force, and then we start adding or assembling. So if we have the delta, is the rate of change of the energy with respect to the force, and we have one component due to the axial. What we notice here is that the axial, we don't have to do integration because it's a constant. dFA by dF is a constant, so there's no integration, so we multiply by the length. And there's a component that is stored in torsion, so we also have this without any integration because it's a constant dt by df. So that's kind of what we note here. The only aspect that we need integration is the moment contribution. So the moments we integrated over the various pieces. So we have one piece from 0 to 7, another piece from 0 to 15, and add up. So the bottom line here, okay, so I go through this very quickly just to mention that number one, you can choose the coordinate in any direction that you want in any, from any end, as long as you keep track of that. Number two, if you do not have the forces or the moments or the torques dependent on the distance, then you don't have to do integration, you just multiply by the length L. Number three, the displacement is only in the direction of the force. So question is that, can we get the displacement in the horizontal direction and the vertical direction? The answer is yes. We can take this value and also decompose it as a vector. So we can have a horizontal component and a vertical component in the plane of the force. In the solutions that you have, there is a different method, a different way where an assumed dummy force is assumed in the x direction, the y direction, each one separately, and then the displacements are computed separately for each direction, and they add up to a vector. So either way is correct. Either you can have the full displacement, decompose it, or you can decompose the force initially and then get the displacement in each direction. So this is a very quick one on the Castagliano. Another one that is interesting, and it comes about in some cases, are the problem of rings. So this problem for ring, we have a ring, and we have a force on one end that is equilibrated by a force in the opposite direction, and the two forces open up the ring an amount delta. So the question is a reverse process. So if we given delta, what is the corresponding force? So that's kind of the idea here. So if we have a ring problem, we have to look carefully at what's going on. Here in this case, we have symmetry, complete symmetry. So we can cut the ring at the mid-plane and then neglect the bottom half and just deal with the top half. So that's kind of a good way to do it, instead of going all the way around and then facing two forces. Here we just have one force, and then the force will create a system at each section, and the system is basically a moment and a radial component and a hoop component. So this is what we call a system. So the system forces is the result of the applied force at the end. So in this case, we take a section here, and then we have applied force. We cut on one end and compute the equilibration of that force. And the equilibration is a moment, radial force, and a hoop force. So hoop force is in the axial direction of the ring. So these are shown here. So each one, moment, radial force, hoop force. And the Castagliano process now is clear to you. You compute those. You take derivative with respect to the force right away. So M is derivative. F, R is derivative. F theta is derivative. And then we have a mixed component, which is a compensation for the moment that is induced by the hoop force. And that we also take as derivative. And then we use the equation that we developed to add up the moment times its derivative, like you can see here. You get 1 minus cosine theta squared. So in these types of ring problems, you always end up with a sine square, cosine square type integrations, as I mentioned before. And those will be provided to you, or we can obtain them from the table or from Google or from any source. So we have one component due to the bending. So the bending, the comment that I have here is this component has a ratio of R over E. And E is the eccentricity. And usually the eccentricity of a thin ring is very small. So R over E becomes very large, like an amplification factor. Contribution. We have a contribution due to the hoop force. The hoop force is axial, so it's 1 over AE. And then we have a contribution. This last contribution is due to the shear force. The shear force is the radial component, so it has a shear factor 1.2. And then this is the mixed moment and hoop force component. So when we go through the integrations, hopefully we would have a table to do that. Then we have the components here, and the point to be made is that the first term is going to win, R over E. You can see here, everything is reduced here, and this is the first term is R over E, so it's very large. And therefore, if you have a thin ring, then we can sometimes ignore all of the other contributions. But if it is a thicker arch, for example, part of a machine that has a thicker arch, then we have to also include the other contributions. So this is kind of a quick rundown of the Castagliano problems that we could have on the final or any other possibility. Any questions?
None here.
Okay. Okay, so if I go to a ring problem, suppose that I have this ring closed, completely closed here, and then instead of having the force on the side, then I have a force from the top here and a force from the bottom opposing it. And I want to compute the deflection in the direction of the force. What would I do in this case? Well, so if you have a closed ring, then the top is going to move down and the bottom is going to move up. And it, again, is very symmetric. Then we can cut it in half and then take the top half. And the top half will be a force on a compressive force on the top, and then what we could do, we just take a section, also compute the moment and the radial force and the shear force. And if it is a thin ring, then we could immediately use the approximation that the bending contribution is going to be the largest, and do the integration here due to the bending by itself. So it can give us the deflection in the y direction, the negative y direction. We have to note here that if this is closed, then it's going to bulge out. So there's going to be a deflection in the x direction and x direction. So when we have the deflection in x direction, then we have to imagine that we have a dummy force, Q, in the x direction, and then compute everything in terms of this Q and take the derivative with respect to Q. So I will leave this for you guys to think about a little bit. If you have a closed ring and then a force on the top and the bottom, can you compute the deflection on the top? Can you compute it on the side? And this will be just kind of a little elaboration on the ring problem that I just covered right now. Okay, so these are comments on Castagliano. Now I just want to give some comments on another problem that comes up in the design. And we started to see some hints of that in in the midterm. And the problem is the following. Given a shaft, and now I want to put some kind of an additional component to transmit power. And this additional component could be a ring, could be a disc, could be a flywheel, could be a gear, as we will see. So whatever we want to put it on there, we have to attach it, as we will see actually at the end of next week. So when we attach, we weaken the shaft. We just have to mill the shaft and put a spline, or we have very many different types of ways of attachments. So each solution has its own pros and cons. Now, one easy solution is the press fit, in which the inner shaft is made deliberately to be a little bit larger than the flywheel in a radius. So the outer radius of the inner shaft is slightly larger than the inner radius of the flywheel. So that creates a kind of an interference issue, and the interference will cause pressure, as we've seen, pressure at the interface. And then as the pressure is imagined to be there, then we can treat both the shaft and the flywheel as pressurized discs or pressurized cylinders. Therefore, we can use solutions from the equations of pressure vessels and pressurized discs, pressurized cylinders. We have those, and we can compute some stress system. Now, the design problem is the following. Given a certain level of interference, we want to judge whether we have this press fit tight enough to transfer some power, some level of power, or level of torque. Well, before we get there, that depends, of course, on the speed of rotation. As the shaft is going to rotate very fast, then there's going to be a force trying to separate the shaft from the flywheel, and at the end it will become loose if the RPM is very high. So we have to guard against that. So this is one design limit at the other end. Like there has to be kind of a maximum RPM, and if we go beyond that, then we will have zero interfacial pressure that is holding the assembly together. Okay, so the solution is, okay, let's actually make the interference very high, because if we have high interference, the interfacial pressure is going to be large, and therefore we can push the assembly to higher and higher and higher RPMs. Well, there's another limitation. If we make the interference very high, then there's a potential problem of failure at the interface. And that is the chapter that we just started to study, and you turn in the homework assignment on failure. And one of the common failure theories is either due to shear, the maximum shear stress theory, or the distortion energy. So that's kind of another limit. In other words, this assembly has two limits: one upper limit at a very high speed, one lower limit, and that is due to potential yield at the interface, or fracture. So you cannot have it both ways. Okay, that's nature. To top it off, on top of this, when we purchase shafts and flywheels, the dimensions are never precise to the last micron. So there's always a statistical distribution around a nominal value. So the nominal value is the mid value of the distribution function. So the distribution function is a Gaussian, and then in the middle we have a number, and that number will be for the ID and for the OD of the members. So that was, I think, if you look at one of the problems in the midterm, we started to touch on that, and we didn't, go into all of the complicated details of assembly, of the design of the assembly, but just we wanted to understand what happens if you have a distribution function. So problem 570, we have a tube that has another tube shrunk over it, and we have an inner member and an outer member, and the ID of the inner member is 1 1/4, and it's plus or minus 3 mils, and the OD of that member is 2.002 plus or minus 4 mils. Now we took the outer member and we put it on top of this, so you can see that the outer member, the ID nominal is 2 inches and 1 mil. So 2 inches and 1 mil is actually smaller than 2 inches and 2 mils. So nominally, if I put these two on top of each other, then there's going to be interference here of 1 mil. And notice some of you or some have assumed that the difference is the delta, but delta is actually the difference in the radii. So we have to see the radii here. The difference in nominally is 1/2 mil, basically, between these two interference. And then you have an extreme, you have 4 mils plus or minus, and the outer is doesn't matter, the outer here, because we're not going to do anything. So what matters is really the ID of the outer and the OD of the inner. So in this kind of problem, we can have the highest stress is going to be when the outer member is the smallest, and the ID of the outer member is smallest, and the OD of the inner member is the largest. So we would have to take the smallest here. We subtract 4 mils from 2.001, and then we add the 4 mils to here, and then take the difference and divide by 2. That will give me the highest possible stress for this assembly. And that cannot exceed the yield, or maybe even not only the yield, but the yield divided by a safety factor for most of the designs. So it's kind of a limitation that we would have on the before we even start rotation of that system. So we have this kind of limitation to guarantee that we don't exceed the yield even in this worst case. But now the problem is that when you start rotating, so let's just discuss this first, finish it, and get into the rotation idea. So if I go here to the solution, we have, this is the nominal interference, is, as I mentioned, 0.5 mil. And then the pressure for every delta, you have it amplified by this factor E over 2R cubed times this factor. And so for every delta, for every 1 mil, you get some certain pressure. For 0.5 mil, you get 3 KSI. 0.5 mil, 3 KSI. So that gives me nominally, that's what's going to happen in this case. And the 3 KSI is now applied as a pressure on, we can use the formulas for pressurized cylinders, and that gives me a tangential component and a radial component. Note that the radial component of the stress is the same in magnitude as the interfacial pressure, just due to equilibrium. And the tangential is usually higher by this factor. So you get minus 7 KSI tangential and minus 3 KSI radial. Now we apply failure theory. So when we apply one of the failure theories, we have a biaxial stress state. One radial, one tangential. We don't have shear because it's axisymmetric, and therefore we can use Mohr circle to get the principal stresses, or basically these are the principal stresses since we don't have shear. And then we can get the von Mises stress and apply the distortion energy criterion with von Mises, and that gives me 6. So we drop them from 7 to 6. And if the yield stress is given, let's say the yield stress is 40 KSI, so we would have a pretty good margin of safety against failure right before we start. But if we take now the other extreme, which is the difference between the lowest, the lowest and the minimum diameter, the minimum radius of the inner diameter and the maximum radius of outer diameter, and divide by 2, then this 3 KSI can jump maybe to 18 or 24, can be pretty high under these conditions. And therefore, when you apply it, then your safety factor could be 1.5, 2. So just kind of reasonable safety factor to start with. So now let's say we started rotating a system. What's going to happen to the interfacial pressure as I rotate the system, and what is the maximum possible RPM that I can expect for that system? Okay, so for that, this situation here, I have a document that I uploaded on this week's material, and this document complements what you have from Shigley, because we need one extra equation for the displacement due to rotation. Like if you look at Shigley, we have the equation 830, one for the radial stress, which is proportional to rho omega squared. Omega is RPM. Sigma theta is also proportional to rho omega squared. These are the two components of the stress in the flywheel or in the shaft. But Shigley doesn't have this last equation. This last equation is a displacement. And we need this equation if we were to figure out at what speed will the shaft be separated from the flywheel. Because initially we have interference delta, but then as the RPM increases, then that interference gets less and less and less, and then at some RPM, then there's going to be the interference will be all taken up by the rotation, and then there's no interfacial pressure in between, and that would be kind of a critical value that can cause failure. So if you the method that we use is superposition, and I gave you the equations for sigma r, sigma theta, and the displacement. The sigma r has two components. One is due to the rotation, and the other one is a result of the interfacial pressure. The facial pressure, just we treat it as a cylinder. And the same thing for the hoop. So these are the first two equations are pretty familiar. The last equation is the new one. So this one is the long part of it is the displacement in a rotating disk that has inner radius A, outer radius B, and the first one is the displacement due to the internal pressure from the pressure vessel solution. So with these, I think we can solve this kind of assembly problem. And an example here is that if you write delta, which is now this 831C, delta at the interface, so you have the component due to the pressure at the interface is the first term, and then the component due to the rotation is the second term. So with that, if we have a value of delta that is given, let's say 5 or 6 mils, then we look at this equation. It has an interfacial pressure, and it has a rotational speed omega. So two parameters. You know one, you get the second one. Okay, so what do we want? We want, for example, the critical speed for separation. Critical speed for separation. Then we put P equals 0, because at that point, the interfacial pressure is going to be 0, and solve this equation for the value of omega that will cause the interfacial pressure to be 0. We can also use it for a design purpose. Suppose that I don't want to go to an interfacial pressure of 0. I want to go up to only 20 20 MPa or 10 MPa. It's a given value that I must use. So I can use the same equation. I put P in it, and then I compute the maximum allowable omega for that assembly to work. So I have this online, and it has a problem that is also solved. So this is a solved problem. Let me see here. The maximum speed of a flywheel assembly. That's what I was talking about. If a contact pressure 20 MPa is to be maintained, find omega. So we use the same expression delta. P now is given as a design variable, is known, and then solve for omega, and then we find the value of omega from this equation. So why am I doing this? Because I think now we have all of the ingredients to solve many different problems but now we're just kind of trying to put them together. This type of example that I discussed, it has so many variations, and in fact, it was given as a comprehensive exam problem, where the exam problem was a design problem. So you're given interferences, you're given limitations, you get materials, you have limitation on speed, limitation on yield, and so forth. So you can see now that this issue of interference and its effect on stress distributions and failure, it becomes very interesting here. Okay, I think that's what I have as material, that prepared material, and I would like to listen to any of your questions now.
Hi, I actually had a question about the project.
Yes.
I keep getting infinite life for my fatigue analysis, and I was wondering if that is something that's okay, like acceptable, or should we not be designing for infinite life?
Yeah, this question comes up quite a bit. I think what we want is actually to design for infinite life, because if you compute the number of cycles to failure for 200,000 and 250,000 miles, it will be in the billions, or maybe 10 billions or 100 billions, very large number of cycles.
Right.
So you need to design for infinite life. However, if you just blindly design for infinite life, the weight is going to be very large. You can always meet the infinite life with a large weight. Mm-hmm. So I think what you want to do is kind of back down until you get the minimum weight that will still satisfy infinite life, which means that you have to thin it down. You have to kind of reduce the size until you get to the borderline of infinite life.
Okay, sounds good. Thank you.
Yeah. Also, later on in the project, you're going to do another check for fatigue design, because you'll see that in the next lectures, where we track a hypothetical crack in the connecting rod. So if you have a little crack on the surface that is below the inspection limit, so the inspection limit will be, it depends on the cost of inspection. We have methods like it varies from ultrasonic all the way to X-rays. X-rays can detect even smaller. But let's say ultrasonic can detect a crack of size maybe 10 mils or so. Then if you start from that and apply Paris law, as you'll see, then the crack is going to grow, and then you might get potential failure due to fatigue fracture if the inspection is not done correctly. So from one side, now you're designing for infinite life using SN methods, but then later you can also design it to avoid the fatigue crack propagation.
Okay, thank you.
Yeah. Any other questions?
Nothing here.
Okay, all right.
I actually had a question on the solution to the shrink fit problem.
Yeah.
I don't understand why the radius R is exactly 1.
Let me get the...
Because when you take the average of the OD and ID nominal, divide by 2, you get an additional 8 10,000. So it's like 1.0008. But the solution here has exactly 1. So I'm just curious as to...
Yeah, you're, I think, okay. All right, there's a good question, actually. Let me go back. So the nominal is not exactly 1. Okay, that's a good question. So I think you can put it in, you know, like you said, but practically, if you do this computation and add the 1.00, you know, 25 and square it, then you will get something like 1 plus 10 to the minus 6, you know, in addition to the 1 on that order. So I think this is just a matter of convenience that they put 1 in the square.
Okay.
Yeah.
Okay.
But it's a generally good question, because in my mind, as a designer, you also have to do things fast. And a lot of times, like in the exam, for instance, we can get stuck with some numbers, and it takes time to figure out how to do the calculation. But this will be an example of how to do it quickly and still, you know, reasonably accurate, you know, this kind of calculation here. The other example I gave is that if you have a ring problem and you have 4 different components and you're going to go calculate everything, but then you know that the energy stored in bending is the largest, then you can ignore everything else and do this part, and you still get 90% of the solution. So the, you know, the expediency is useful sometimes in design applications.
Okay, that makes sense. Thank you.
Okay, any other questions? All right, so I think we're in good shape, and then if you guys need any additional help, I think you is going to review the challenging problem that we put together on the final. I think most of you did okay, but there was a challenge in it, definitely, because you had a force at the junction between a thin section of the shaft and the thick section, and that caused the moment diagram to the moment over I diagram to be kind of challenging. M itself was okay, everybody got the M, but then M over I using singularity function. That's the thing, is that if you didn't use singularity functions, you can divide up the shaft into pieces, 3 different pieces. But if you do that, then you have to have constants of integration on every piece, and then you have to kind of piece them together and solve for 6 constants, which is not really very nice. So the idea is to use singularity functions, because it gives you like one equation for M over I. But that equation has 1 drop at the junction on both sides, 2 drops actually, and a change in the slope in the middle. So he prepared the solution, and he's going to also discuss that. Okay, so great. We don't have, if no more questions, we finish with the with this office hours, and I'll see you next Saturday.
Thank you.
Thank you.
Thank you, Professor.
Okay, bye-bye.
Take care.